Here in 6.6, we're going to continue graphing sine and cosine functions. Now we're looking at horizontally and vertically translating them. So we've already graphed functions of the form y equals a times sine or cosine of bx, right? And we saw that the b value associated with the function affected the period of the graph. So we saw that the period was always equal to 2 pi divided by that b value, or 360 degrees divided by b. And then the amplitude of the graph was affected by our a value. Amplitude was always equal to the absolute value of a. All right, so nothing changes with regards to those two parameters. Now let's say we want to take those functions and we want to translate them horizontally h units and vertically k units. Then the equations have to be altered, all right? They have to turn into something like these. So to get the horizontal translation h units, we have to subtract that value of h from x within the function. And to get the vertical translation of k units, we just have to add k to the function, all right? Now the horizontal translation is often referred to as the phase shift of the function. So we see phase, we're thinking horizontal here. And again, that's just based off of the h value, okay? The vertical shift would be based off of the k value. Now let's dynamically illustrate each of these. All right, so here I have a cosine function right now with a period of 2 pi and an amplitude of 1, okay? And if you look at the sliders over here, there's sliders for a, b, h, and k. So right now a equals 1, that's making the amplitude of this curve 1 unit. B equals 1, which makes that period 2 pi, but then notice h and k are both set at 0, so there's no shifting that's taken place yet. Okay, so right now this is just your parent function for cosine. We know that if I change the value of a, the amplitude changes. That's a vertical stretch or compression taking place. If I change the value of b, the period changes. That's going to be a horizontal stretch or compression. And then notice if I change the value of h, the graph's just going to shift horizontally left or right. If I change the value of k, the graph just shifts up or down, which has an effect on where the midline of the function is, all right? Okay, so now let's go ahead and graph some equations ourselves, all right? So graph one period of y equals 1 plus 2 times sine of theta, all right? So based off of this equation, I would say that my a value is 2, my b value is 1, the h value is 0, and the k value is positive 1, all right? So the amplitude is going to be based off of that a value. It's 2 units. The period is going to be 360 degrees. Notice I'm going to use degrees because look at the graph that's labeled here. It's in terms of degrees. So the period's 360 divided by my b value of 1, so that's remain 360, right? The phase shift would be 0 degrees. That's because h is 0. And then your vertical shift is going to be based on your k value of 1. So that just, since it's positive, that just means we're going to move up 1 unit, which ultimately has an effect on the midline. It's now going to move from the x-axis up to y equals 1. Okay. So the first thing I'm going to do to make my graph is I'm going to draw in that midline. All right. And now I'm going to focus on the period of the function. The period is 360, and I'm going to divide that by 4 to give me 90 degrees, and that just tells me how far apart all of my critical points are spaced horizontally on the curve. Okay, so normally the sine function starts at the origin, right, for the parent function. Well, now it's going to start 1 unit up to where it's now at the point of 0, 1, right on that midline, okay? Now, from that point, you're going to move 90 degrees to the right, and you're going to move 2 units up based off of the amplitude. So that's technically the point of 90, 3. Then you're going to move 90 degrees to the right, or 2 spaces, and back down to the midline. That's your third point. Then 90 degrees to the right again, or 2 spaces, and then 2 units down. So that's at 270, -1, and then 90 degrees to the right, back up to the midline. Okay, so there's one full period. And we know that, of course, it would continue on either end. Right? Second example. Now we graph y equals -1 plus the cosine of 2 times the quantity theta plus 90 degrees. All right, so here I would say that my a value is 1. That's because there's nothing multiplying the cosine function. I would say my b value is 2. H would be -90 degrees, or -90. And then k would be -1. All right. So your amplitude here is 1 unit. Your period, which I'll use in degrees again, is 360 degrees divided by the b value of 2, which is 180 degrees. Your phase shift is going to be based off that h value. It's -90 degrees, so that means we're moving left 90 degrees. And your vertical shift is based off of k, which is -1, so that means down 1 unit, and that moves the midline from the x-axis down to y equals -1. All right. So this time, to start my graph, I'm gonna draw in my midline, and I'm gonna draw in a vertical line as well, based off of the phase shift being at -90 degrees. Okay. And I want you to think of the intersection of those 2 points, or of those 2 lines. Think of that essentially like your new origin after the shifting has taken place, okay? And now I'll take my period of 180 degrees, I'll divide that by 4, which is 45 degrees, okay? So I know that all of my critical points for this curve should be 45 degrees apart horizontally, all right? So first point I'm going to plot is going to be based off the fact that this is a cosine function, and the cosine function normally starts 1 unit above your midline, right? So in this case, my first point that I'll plot is right here, okay? Notice it's 1 unit above the intersection of the 2 lines that accounted for the phase shift in the vertical shift, okay? Then I'm going to move 45 degrees to the right, which is 1 space on this particular grid, and back down to the midline. 45 degrees to the right, 1 unit down. 45 degrees to the right, 1 unit up. 45 degrees to the right, 1 unit up. So right there's one full cycle, and then just repeat the pattern. All right, and there's our curve. And of course, if you want to make certain that these are the proper points for the function itself, just pick a random point and plug its angle measure into the function and evaluate it to see what the y is, and make sure that it corresponds to the y coordinate of your point. Okay. All right, one final example. Here we're graphing y equals 1 plus 3 times the sine of 3x minus pi over 2. And what we want to notice is that the argument of this function, which is 3x minus pi over 2, that argument is not in the form that we need it to be in, okay? We need it to be so that x is being added or subtracted by your number and then being multiplied by the value in front of x, okay? So we're going to have to rewrite this by factoring out a 3 from that argument. And it's going to turn it into 3 times the quantity x minus pi over 6, right? If I take a 3 out of pi over 2, it results in pi over 6, okay? So now I would say my a value for this function is 3, my b value is 3, h is pi over 6 now, and k is 1. That's going to make my amplitude 3 units. My period would be 2 pi divided by the b value of 3. Okay, so the period's 2 pi over 3. The phase shift is going to be positive pi over 6, which means move right pi over 6 units. And the vertical shift is going to be 1, meaning move up 1. And that moves the midline to y equals 1. Okay. All right, now notice the grid that I have supplied here, I don't have it labeled right now. Okay, and to me that's one of the main parts on this example we want to focus in on is how to properly label this based on the parameters of the equation, okay? It's all going to be based off period. So the period for this function is 2 pi over 3. I've taught you to divide that by 4, so you know how far apart to space your points horizontally, right? So dividing by 4 is the same as multiplying by 1/4, and that's going to give me pi over 6, okay? So for this grid, I'm going to label the x-axis in terms of pi over 6, okay? So this first grid line in the positive direction is pi over 6. The next would be 2 pi over 6, which is pi over 3. Then 3 pi over 6, which is pi over 2. 4 pi over 6, or 2 pi over 3. 5 pi over 6. And then 6 pi over 6, which of course is pi. And then we could do that in the negative direction as well. Negative pi over 6, pi over 3. The y-axis I can just label by 1s. All right. Now let's take the shifts into account. So the vertical shift moves my midline up 1 unit, and the vertical shift was pi over 6 to the right. So again, let's think of the intersection of those two lines, kind of like our new origin. And the sine function always starts at the origin, right? Its first point is at the origin. So we're going to place our first point at the intersection of those two lines. Then we're going to move 1/4 of the period to the right, which is 1 space in this case. And we're going to go 3 units up based on the amplitude being 3. Then 1/4 of the period to the right, back down to the midline. 1/4 of the period to the right, down 3. 1/4 of the period to the right, back up to the midline. So there's one full cycle, and then let's just fill up the graph. And there's our curve.